we'll start looking at the laws of thermodynamics, and these laws are the things that govern virtually every process, everything we'll be looking at. So today I'm just going to briefly look at, so like I said, two things I wanted us to attend to today. One was if there was any question, which I've waited for a bit and none has raised any question. And then secondly, I'm going to run through some theoretical things today, and then I'll make a recording similar to what we did last week. I'll make a recording for the calculations just to consolidate the theory. It could, I mean, from what I've tried, I'm going to keep trying again, but it's been quite difficult trying to share the screen where I write alongside with this screen. So I'm going to do the recording, and I also want to believe that with the recording, it's that I sent to you for the calculations, you're able to pause and play, you're able to do so many things in your own time, in your own space. So that's why I've been using that. But like I keep saying, if you have any concerns, any query, any questions, please raise them. So today we'll be looking at the two of the laws. Oftentimes the first law and the second law are talked about, but zeroth law also needs to be talked about. And we'll see the reason why we need to talk about the zeroth law of thermodynamics. In the last class, we've seen two main types of energy. These are the energy types you are very familiar with from physics, chemistry, elementary physics, chemistry, things we did in high school, things we did in first year, which are potential energy and kinetic energy. But these two types of energy, kinetic and potential, are regarded as external. So they are regarded as external. One, the reason why they are regarded as external is they have to do with your system in reference to a point, your system relative to a reference point. So for example, you talk about your kinetic motion. So you can't talk about a kinetic motion, I mean kinetic energy rather, if there was no motion, if there was no movement. So you talk about movement from point A to B. So there's a reference point. So it's something, so that's why it's external. And then same for your potential energy. It's also external in the sense that you remember you talk about it's elevated. You have a system, you have a body that is elevated from a particular height. So there is a reference point. So those two types of energy are called external. Another thing about potential and kinetic energy is they are also referred to as macroscopic. When you say something is macroscopic, it means you can see. So you can see something is moving. You can see you can see the body or the system. You can see that it's high, it's on an elevated place, so it's macroscopic. So I've spoken about two things now, external and macroscopic, defining the potential energy. And now but there is another type of energy which is both internal, is referred to as internal energy, and it's also referred to as being microscopic. The reason why it's referred to as microscopic is it's a sum total of the energy of molecules or particles contained in a system. So think about it, any system, a block of material, whatever system it is, it might be solid, it might be fluid, it might be liquid. That solid is made, that matter, that material is made up of different particles. So those different particles, which we can refer to as atoms, for example, they have different energies in them. So they are, for example, they can have bond energy, that the different atoms are used to come together, or the different molecules used to stay together. So they can have that. And then you can also have within those particles, individual particles can move. So that means those individual particles also can have individual kinetic energies. And then they can also have, because they might also be suspended within, that means they can also have potential energies. So take note of that. We are talking about internal energy now. So it is microscopic, you cannot see it. And it is internal because you're dealing with particles, you're dealing with atoms within the system. So that is your internal energy. And oftentimes is this internal energy that we use to define heat. So it is this internal energy that we use to define heat. So excuse me. So heat is not an energy. So from the perspectives of thermodynamics, heat is not an energy. So let me go back again. So we've said there are three, we can talk about three types of energy. And these three types of energy can be classified differently. And what are these types? We have the two types that are classified as both macroscopic and external. Those are potential and kinetic energy. And then we've got one, which can be classified as internal and microscopic, because you cannot see the particles, you cannot see the molecules, you cannot see the atoms, but they possess internal energy. So it is the transfer of this internal energy that results in heat. Remember, we are talking about thermodynamics, so we'll be talking about heat. We're talking about temperature. So it is the transfer of this energy, of the internal energy, that we refer to as heat. So heat is not energy, it's the transfer of energy. So imagine you have two bodies. For example, I've got my cup of coffee here. I'm sure many of you also do. You've got your cup of coffee and your cup of tea. And I'm holding it in my hands. My hand wasn't hot originally, but now with me holding it, my hand is feeling warm. So there is a transfer of energy from the cup to my hand. So that transfer of energy has resulted in heat being generated in my palm. So that is heat. Heat is not energy, but transfer. So that's one thing you want to take note about heat and internal energy. So there is an internal energy in, so for example, in my coffee, you can't see the particles. You cannot see the water, you cannot see the coffee, you cannot see any of those things. So it is microscopic, but inherent in it, those particles are moving. So as the particles are moving, heat has been generated. So the heat is now being transferred from a place of high temperature to a place of low temperature. So my palm was not warm originally. So it was a place of low temperature. The cup of coffee was warm. I mean, it's still a bit hot. It's a place of high temperature, and then there has been a transfer. So that transfer of energy is what we refer to as heat. And so take note of that. So heat, transfer of energy, not energy itself. And then we said the heat is as a result of the entropy movement taking place within the particles. So those are things that I want us to quickly take note of when it comes to heat, when it comes to energy. All right, so we've talked about those different types of energy. Let's moving on. So let's start with the zeroth law of thermodynamics. So we have zeroth law, we have the first law, we have the second law, and then we'll be talking about those. We'll be unpacking those ones one after the other. So the zeroth law, this is what it simply says, and you like I'll keep reiterating, as much as possible, don't cram things. Try and understand what they mean. And then you might be wondering, we do theory, we do calculations. Yes, is the theory that underlie the calculation. So if you don't understand the theory, so for example, if you have a calculation, if you don't know the theory, you'll not be able to know, is it an isobaric system? Is it an isothermal system? Is it what kind of system am I dealing with? Because you need to know the system or the process for you to be able to use the appropriate formula. All right, so back to our story. So you have two bodies separately in so they are separate, they are not in contact. Previously, I've explained contact with you in terms of heat, but you can also have exchange of heat. You can have heat exchange when two systems or two bodies are not in contact. So if two bodies are separately, so we have, these are bodies B and C in thermal equilibrium with a third body. What's the meaning of thermal equilibrium? They are in the same state. So for example, let's assume I hold this that's going to be difficult actually with my hand, but let's just assume that the coffee inside is a body, and then the mug is another body, even though in this particular case they're in contact, but let's assume they are not in contact. What will happen is, remember, the heat that I'm feeling on the mug is actually coming originally from the coffee inside. So what happens is that there will be, over time, there's going to be an equilibrium between those two bodies. So body B can be in equilibrium with body A. C can be in equilibrium with body A. So remember, it's just like in mathematics, you talk about if A is equal to B and B is equal to C, then A must be equal to A must be equal to C, B must be equal to C. You get the gist. So B is in equilibrium with A, C is in equilibrium with A. So then we say automatically B and C must be in equilibrium with each other. So if B is in equilibrium with A, C is in equilibrium with A, then we can say B and C are in equilibrium with each other. This can be summed up in another way. So let's say A is replaced by a thermometer. So what does this mean? It simply means that the two bodies are in thermal equilibrium with each other. So can I say that again? Remember, it was B that we said originally was in equilibrium with A, not with C. C was in equilibrium with A separately, B was in equilibrium with A separately. But we are now saying that because of the fact that they have that common denominator, if I might call a common denominator, B and C must then be in equilibrium, thermal equilibrium with each other. So that was why we said, for you to understand it better, let's rather say we put a temperature, in between. In thermodynamics and in chemical engineering or process engineering generally, we will put something we call heat exchanger. So there might be something called heat exchanger between these different bodies to transfer energy from one point to the other, to transfer energy from one point to the other. I'm also trying to check the chat panel every now and then in case someone decides to write is your question there. So please don't forget, raise your hand if you have a question so that I can pause along the way. So that is simply what the second zeroth law is about. Let's move on to the um, first law. So the summary of the first law is that energy can be transferred. Energy can be transferred. Energy can be transformed, but energy cannot be destroyed. Energy can be transferred. Energy can be transformed, but energy cannot be destroyed. So that is the summary of the first law of thermodynamics. So remember, we cited an example last week when I showed a pot on a thermal plate. So the thermal plate was being powered by electricity. So that was electrical energy, which was converted to heat. So the same amount, the heat was then converted to kinetic energy based on the internal energy of the water molecule. So there were bubbling, there was kinetic energy in the water particles. So you could see there have been a transfer from electrical energy to thermal energy to kinetic energy in that example. So all this, the energy can be monitored. So we can monitor the energy. We can say there was a transfer from the surroundings. We can use the electrical plate as the surroundings, and we use the pot as a system. So there have been a transfer from the surroundings to the system. And the vice versa can also happen. there can be a transfer from the system to the surroundings. So there can be a transfer from the system to the surroundings. So that is what so that is a summary of the first law of thermodynamics. So mathematically, we say a change in E in the energy of the system is equal to the change in energy of the surroundings. And if you remember, please carefully go through the examples that I worked out last week. You see there, we said in certain cases, we indicated if, for example, if the system is gaining energy, we'll say it is positive. If it's losing energy, we say it's negative. So you need to be able to denote when something is positive, when something is negative. So that is that, the change in total energy of the surroundings. And take note, is the total energy we are talking about now. So that was why I started by talking about internal energy. So we first look at the total, because we'll be looking at total energy in a moment, because the total energy constitutes the different types of energy we've talked about. Can you just give me a moment? I just needed some internal energy, so I just sipped my coffee. So remember, we've said the issue of the first law of thermodynamics have to do with transfer. It has to do with transformation of energy. It has to do with transfer of energy. It has to do with transformation of energy. So if it has to do with transfer of energy, so it also means that we need to be mindful of what kind of system do we have? What kind of system do we have? You remember we saw in the previous classes, we have closed system, we have open system, and we have what we call isolated system. So in the closed system, there can be transfer of energy only, no transfer of matter. So there is no transfer of material. So there's transfer of energy only. So based on that, we can come here to say the total internal energy from the system, closed system, is equal to the energy from the surroundings. So let's look at this. So change in energy of surroundings, we say plus or minus, and I've indicated how we know that. So if it's going to be plus, if it's a gain, it's going to be minus. If it's so it's going to be plus if it's a gain in energy. So it's going to be plus if it's a gain in energy, it's going to be minus if it's a loss in energy. So energy of the surroundings. And then we have the energy of the system. So U, this is our internal energy that we talked about earlier on, internal energy. And then we have our kinetic energy and potential energy. So take note, change in internal energy, change in our external energy. And remember, these two make up our external energy or the macroscopic energy. So that makes, so you equate that, and then I'm sure to make more sense when we start, when I work out some examples. So that it means that changing that equals to that. So this summarizes the first law of thermodynamics. So in terms of, so mathematically, the first law of thermodynamics is that. So I've described the first law of thermodynamics to us theoretically, but we are saying that mathematically, this is how it is represented. And this is for a closed system. Remember, we said in a closed system, material is not transferred, but the energy can be transferred. So we said sign convention, when transferred from surroundings to the system, what is that telling you? The system is gaining energy. And then it is negative when transferred from system to surrounding. So for example, my cup of coffee, let me use that example again, is getting warm. It was hot at the beginning, but it's getting warm. So what is that? What is happening? It is transferring, the body or the system is transferring energy to the surroundings. So since it's transferring energy to the surroundings, it's getting cooler while the surroundings is getting hotter. So for the heat transfer from the cup of coffee is going to be negative, and then for the surroundings, where I'm teaching you from, it's getting warmer, so it's going to be positive. So this equation tells us that total energy change of a constant mass. So take note, constant mass. Why are we talking about constant mass? Can tell someone give me an idea why we're talking about constant mass system here? You can either unmute yourself or you write it in the chat. Why for this particular system? Why constant mass? Any takers? Why constant mass? If you can either, so please, it's no question is foolish. Any question, I mean, sorry, no answer rather is foolish. I believe any answer will go a long way. So any takers? Okay, is someone writing? Is someone answering in the chat? Let's see. Thank you. Thank you. Thank you. I'm good. So glad to hear that. So thank Arisha, ShopRite. I don't know someone's name on system is ShopRite. Thanks, ShopRite. I've not seen Pick and Pay and Woolies here. Since we have ShopRite, I would expect for us to have those. Yeah, thanks, Blom. Yeah, so everyone that has answered, you're right. So because it's a closed system, there's no exchange of matter. So that is why we call it a constant system. So thank you for that. Yeah, thank you, Zippo, as well, all of you, Kwanele, everyone that has responded. So let me just get back to my slide. Just give me a moment. Okay. All right. So we are all on the same page. I'm so glad to hear that. So at least to see you're following me. So and then we have when in a steady system as well, it's going to be a different case. And I'm trying to take this off the screen. So for a steady state system, there is a non-flow system. So when you talk about a steady state, so take note of that. In a steady state, there is no flow. And whenever we're talking about flow, we can refer to flow as transfer as well. So when you talk about a flow, you talk about the flux, you talk about movement from one point to the other. So if there are no movements, you have a steady state. So it's non-flow. So if it's non-flow, we have change in U, Q, so we have that. So we have that summation. And then we also have for a cyclic system, it equals to 0. So those are some of the equations we'll be encountering when we look at calculations. So I'm going to walk through these examples. Quite a number of examples that are here. So what I'll try to do is walk through as many as possible, and then I'm glad to see the kind of conversation and discussion I saw on the platform last week. So please, let's get this going. I left question 5 on attended to, and quite a number of people attended attempted it, which was quite impressive. So let's please continue with this. And okay, so I'm going to try and address as many questions as possible and then leave the rest. And then please, class rep Thami and Cloma, please remind me. I also need to introduce you to the teaching assistant. We are supposed to have tutors. I'm still waiting on the department on that. So I need to introduce you to those as well, so that you can get the appropriate help from all the sides, from me and from all the sides. So from me and all the sides, I see someone wrote a Selima there. Please, if that is your surname, please write it properly. If you're trying to fill the register, write it properly. It should be your surname and the initials. Thank you. All right. So enthalpy. So enthalpy is also enthalpy is used to describe energy transfer between a system. So enthalpy can be used to describe energy transfer. It's used to describe energy transfer as well. So that from a system to the other. Remember last week we looked at the PV relationship. So enthalpy sums looks at the relationship between PV, the PV relationship, and your U. And remember, we said your U is your total internal energy. And then, so that means we can also look at what is happening to, we can calculate heat transfer based on what is happening to pressure and volume. So using enthalpy, we can look at what is happening with, so we can find a relationship between heat, energy, pressure, and volume. So that is what our enthalpy is providing us. So enthalpy is providing us the relationship between heat, the energies. We've talked about the different types of energies. We've talked about total energy, and then the PV relationship, pressure and volume. So since we have, so that is what enthalpy does. And then so we have a total energy. Let's think about total energy in a system. We can look at different systems. We can look at a system where the pressure is constant. Remember, when the pressure is constant, what do we call the system? What's the name for a system where the pressure is constant? Any takers? Also, Zippo is asking, does the first law of thermodynamics, is it dealing with closed system only? No. So it deals with closed system and open system. I hope that, yes, yeah. So it deals with closed system and open system. So that was why at the beginning I said, so when we are dealing with thermodynamics, so we need to look at which systems do we have transfer. Remember, in the isolated system, there are no transfers. So we cannot talk about first law of thermodynamics for isolated system, but we can talk about it in closed system and in open system. So I hope that answers your question, Zippo. And yeah, I've gotten responses from a couple of people again. So constant pressure, isobaric. Thank you. That's impressive. So let's move on. So in an isobaric system, so we can have that. So that's why I want you to start having those things at the back of your mind, so that when you have a list of equations, then you'll be able to ask yourself, is this an isobaric system? Is it an so what is it? What kind of system am I dealing with? So it's this kind of system that I'm dealing with that's going to determine what tool that I'm going to use. So think about, you have a list of equations, it's a toolkit, and then you need to be able to understand, what problem am I facing? Does it need an hammer? Does it need a screwdriver? What does it need? I don't want to use I don't want to be using I shouldn't be using hammer on a screwdriver. I'm using a screwdriver on a nail. So I need to be able to use. So that's why I'm trying to go through this theory. So differential equation depending on this. So if at constant pressure, the equation will change. So thus, when a system is heated at constant pressure, or an isobaric system, the only expansion that occurs, we use it. We use change in enthalpy to describe that. So that is what that is for. So I'm going to leave those other things for you to look through. So another example, for a couple of other examples to walk through. So Zippo, you preempted where we were going, and I like that. So Zippo asked, does it does it deal with closed system only? So we are seeing that no, it also deals with the open system. So in an open system, we can say there's an influent, there's an effluent, there's an inflow, there's an outflow. So there's a movement because it's open to the atmosphere. So for example, my cup of coffee, again, it's an open system. So it's open to, so it will become a closed system. For example, if I had it covered, but I had it covered. So obviously, if I had it covered, I'm not going to be able to transfer. That is, you remember when it was open, like now, I'm able to transfer, I can drink from it. So there'll be a matter transfer of material. So that's an open system. So in this system, there's an open system. So because it's an open system, we are going to see that the way we deal with the internal energy is going to be different. The way we deal with the total energy is going to be different, because at different state in the system, the material would behave differently. Remember, there's a transfer, there's a movement of material, there's an exchange of matter. So the matter is going to behave differently at different points. So we need to be able to take note of how does it behave here? How does it behave there? How does it behave here? So it's going to behave differently at different points. So that is why the system, so that is why we need to be able to identify what system are we dealing with. So I haven't said that. So the system is taken as a unit mass of fluid as it flows. So we've seen the apparatus from section 1 to section 2. So remember, we said from section 1 here to section 2. So what happens in section 1 is different from what is happening in section 2, and there's something happening in between as well. So the system is taken as a unit. We've said that the energy of the unit, okay, so let me just leave those theories for you to read through. So according to the first law of thermodynamics, the total energy with which the fluid is entering at section 1 plus the energy imparted to the fluid while in the system. Remember, I mentioned earlier on there's something we call heat exchanger. So there is an impartation here. So there will be an additional, and remember, so there will be additional heat here, but heat exchanger can work either way. So our Q can be positive or negative. So if it's negative, what is that? What is happening? That will be, if it will be negative, let me get my pen out again. It will be negative if this is the direction. So the heat exchanger can be taking heat out of the system as well. But in this particular case, we are saying that it's taking heat into the system. So there's an additional heat. So we look at that. So at each state point, the energies involved need to be looked at. So you could see we've added another thing here. While we've looked at every other energy, we've talked about potential, kinetic, internal, we are saying there's another one, flow energy, because there is a push. So there is a push. So there is a flow taking place there. So this is what this is further telling us is that we, apart from those three types of energy we've talked about, there are some other minute types of energy that we might consider. But these other minute types of energy, they are still related to these three. They are still related to these three. And also, if you remember, you see, we saw earlier on that even this one is related to these two. The only difference is that these two are macroscopic and this one is microscopic. And then we said that this one is microscopic, and within the micro scale, you have potential and kinetic in the micro scale, and then we have potential and kinetic in the macro scale. So what am I trying to say? You can always relate these different types of energy together. So if you know these three main ones, you can always get to the other ones. So at section 1, we have the total energy constitutes that potential energy. Remember, the fluid is above the point, a point of reference. So there's a potential energy. So as it begins to move, there's a velocity. So there's kinetic energy. And then entrance work, there's a flow energy. So remember, as I mentioned earlier on, there is a work being imparted. Are you beginning to see now the PV relationship? We saw that also in the previous class where we related that to work. So there's work taking place, which is related to the PV relationship, or which we also saw in the closed system, the PV relationship relating to enthalpy, when you have a transfer. So in this case, because there's pressure, it's not an isobaric system, the pressure will be changing. So the pressure at that high point is different from at low point, will be different at the exit point. So the pressure will be changing. So then we can sum up all this. So U, we've talked about what U is, internal energy. We've talked about what mgz is. We looked at it previous class. your potential energy, half mu squared or mv squared, your kinetic energy, and pv squared, that is your flow energy. So we have those, section 1, section 2, and then we can sum up all of them together. So I'm going to leave you with that as well, but I just want you to catch the drift. So that's how we do that, and then you can go through all those other theoretical things, and then I'll try and work out the as many examples as I can. So for a fluid substance, so a fluid substance meaning it's flow. If it's a fluid substance that is flowing, and so it in an open system, so we are going to have, so I'm going to quickly check. I want to keep pausing if to keep checking if there are questions. All right, none. So we have all this. So I'm going to leave this here as well. There are things that are self-explanatory. I don't want to bore you with too much of the theory. While on Zoom, so there are things that are explanatory. They are based on everything that I've tried to explain. So there is reversible processes. You could see this also just talks about the theory. It talks about different things, reversible. When you say something is reversible, it can move from one point to the other. So this is where I'm going to stop for today, and because I've tried to establish the fundamental things, and I'll try and do the calculation as soon as possible so that I can have them on the different platforms. So I'll put them for the videos. The reason why I've been putting, it's difficult for me to download the video for you on WhatsApp, is because oftentimes the video are large. So that's why I put the recordings on Blackboard. I put the videos that I generate. I put them on YouTube. I put them on, so that I put them on Blackboard as well, so that you can access them from different points depending on the one that works for you. So I'm going to stop sharing at this point, and then I'm going to take attend to any question, and if there are people that